Assalamu alaikum, brothers and sisters. Welcome to the journey of quest, where we quench your thirst of knowledge. Ever wondered why ice melts or why your coffee cools down? It's all about the science of thermodynamics. This fascinating field of study is about much more than just heat and temperature. It's a fundamental branch of science that deals with the principles of energy, heat, and work. Imagine, if you will, a world without thermodynamics. We wouldn't understand why certain chemical reactions occur, or why others don't. We wouldn't be able to predict the behavior of gases under different conditions, nor could we explain the workings of engines and refrigerators. Thermodynamics allows us to comprehend and predict the outcomes of chemical reactions, and it's vital for everything from designing energy-efficient buildings to understanding the human body. So without further ado, let's dive into the fascinating world of thermodynamics and chemical reactions. Before we move on to how pure phases interact with thermodynamics, let's take a closer look at what exactly a pure phase is. As we mentioned earlier, a pure phase is a substance that is both homogeneous and physically distinct. But what does that really mean? Well, a homogeneous substance is one that is uniform in composition. That means every single part of it has the exact same properties. And when we say a pure phase is physically distinct, we mean it's separate from its surroundings. It's its own entity, so to speak. Now let's talk about phase diagrams. These are graphs that show the conditions under which a substance exists in a certain phase. They're incredibly important because they allow scientists to predict the phase of a substance at any given temperature and pressure. And one of the most intriguing points on a phase diagram is the triple point. This is the unique set of conditions at which all three phases of a substance, solid, liquid, and gas, can coexist in equilibrium. It's like the perfect balance of temperature and pressure. So pure phases are more than just uniform substances. They're a crucial part of understanding thermodynamics. They help us understand how substances change when conditions like temperature and pressure are altered, and they're key to predicting how a substance will behave under different conditions. In our next scene, we'll delve deeper into the fascinating relationship between pure phases and thermodynamics, so stay tuned. Picture a block of ice. It's a perfect example of a pure phase in thermodynamics. In the realm of thermodynamics, a pure phase is a substance that is homogeneous and physically distinct. Picture the ice again. It's homogeneous because it's made up of the same water molecules throughout, and it's physically distinct because it's separate from its surroundings. Now let's talk about energy flow in a pure phase. Thermodynamics is all about energy and how it moves from one place to another. In a pure phase, like our block of ice, energy can flow uniformly due to the consistent nature of the material. The ice will cool your drink evenly because the energy in the form of heat is being transferred uniformly across the ice cube. But here's where things get interesting. What happens when that ice cube starts to melt or when water begins to boil? These are examples of phase transitions, which is when a substance changes from one state or phase to another, like from a solid to a liquid or a liquid to a gas. Phase transitions are part and parcel of thermodynamics. When heat is applied to our block of ice, it gains energy. The molecules start moving faster. They break free from their ordered structure, and the ice turns into water. A phase transition has occurred. Similarly, when you heat water to boiling point, it gains enough energy for the water molecules to break free entirely, becoming a gas. And it's not just about adding heat. Phase transitions can also occur when pressure is applied or removed. This is why water boils at a lower temperature at high altitudes, where the air pressure is less. Thermodynamics is more than just a study of heat and work. It's about understanding how different forms of energy cause changes in our world, right down to the phase transitions of the simplest substances. The next time you watch ice melt or water boil, you'll know there's more to it than meets the eye. Let's sweeten the deal with a deeper understanding of ideal solutions. As we discussed, an ideal solution is a perfect model that helps us understand the principles underlying real-world solutions. But what makes them so ideal? Let's delve a bit deeper. Remember Raoult's law, which states that the vapor pressure of each component in an ideal solution is proportional to its mole fraction? This means, in our sugar tea example, the vapor pressure of the sugar and tea are just right, creating a harmonious balance, much like the perfect sweetness of your tea. Now, let's stir in the concept of ideal gas law. Ideal gas law is a fundamental principle in thermodynamics that describes how gases behave. While it might seem unrelated, it's actually closely tied to our understanding of ideal solutions. The ideal gas law states that the pressure of a gas is directly proportional to its temperature and volume, and inversely proportional to the number of gas molecules. Similarly, in an ideal solution, the properties of the solution are directly related to the properties of its components, just like the sugar and tea. But it's not all sweetness and light. Real-world solutions also have properties that depend solely on the amount of solute present, irrespective of its identity. These are called colligative properties. They include boiling point elevation, freezing point depression, vapor pressure lowering, and osmotic pressure. In an ideal solution, these colligative properties are directly proportional to the mole fraction of the solute, such as the sugar in your tea. Ideal solutions are not just theoretical. They're a sweet reality in the world of thermodynamics. So the next time you're stirring sugar into your tea, remember that you're not just sweetening your beverage. You're also creating an ideal solution, perfectly balanced and full of thermodynamic principles. Imagine you're mixing sugar into your tea. You've just created an ideal solution. An ideal solution, in the realm of thermodynamics, is a bit like the unicorn of solutions. It's a theoretical construct, a perfect model that exists to help us understand the principles underlying more complex, real-world solutions. In this perfect world, every molecule of sugar interacts with the tea in exactly the same way as it does with other sugar molecules. And every molecule of tea interacts with the sugar in the same way as it does with other tea molecules. Sounds a bit like a utopia, doesn't it? Well, this is precisely what makes it an ideal solution. Ideal solutions obey Raoult's law, which states that the vapor pressure of each component in an ideal solution is proportional to its mole fraction. However, reality is a bit more complicated. Real solutions don't always behave as nicely as their ideal counterparts. They can veer off course, not following Raoult's law due to differences in molecular interactions. But don't worry, the concept of an ideal solution gives us a good starting point to understand these deviations. Now let's stir in some entropy. Entropy, essentially a measure of disorder or randomness, plays a leading role in the formation of ideal solutions. When you mix sugar into your tea, the sugar molecules spread out, increasing the disorder of the system. This increase in entropy is what drives the formation of the solution. In an ideal solution, the entropy of mixing is always positive, signifying an increase in disorder. The process is spontaneous and no external energy is needed to make it happen. It's a bit like teenagers at a party. Given the chance, they'll naturally disperse and mingle, creating a healthy dose of chaos. So, that sugar in your tea isn't just making it sweet. It's also a perfect example of an ideal solution in action. Ready to stir things up? Let's dive deeper into the fascinating world of non-ideal solutions. Non-ideal solutions are the rebels of the solution world, not playing by the rules. They deviate from Raoult's law due to differences in molecular interactions. But how can we understand these deviations better? That's where azeotropes come into the picture. Azeotropes are special types of mixtures that behave as if they were single components. They boil at a constant temperature without changing their composition, defying the expectations set by Raoult's law. They're like the renegades of the solution world, always keeping us on our toes. Now let's talk about deviations. In non-ideal solutions, deviations can be positive or negative. Positive deviations occur when the interactions between the different species are weaker than those within the same species. The result? More volatility and a higher vapor pressure than predicted by Raoult's law. Negative deviations, on the other hand, occur when the interactions between different species are stronger. This leads to less volatility and a lower vapor pressure. It's like a tug of war between the molecules, each pulling in their own direction. But how do we separate these deviant mixtures? That's where fractional distillation comes into play. This process separates a mixture into its component parts based on their different boiling points. But remember, this can be tricky with azeotropes as they boil at a constant temperature. So, non-ideal solutions are not just complex, they're a fascinating part of understanding thermodynamics, reminding us that not everything is as it seems. Remember, in the world of thermodynamics, complexity is just another word for fascinating. But not all mixtures are as simple as sugar and tea. Welcome to the world of non-ideal solutions. When we talk about solutions, we're often referring to ideal solutions, those that follow Raoult's law perfectly. But what happens when we step out of the ideal world? That's when we encounter non-ideal solutions. These are the mixtures that don't follow the rules, the rebels of the solution world. Non-ideal solutions deviate from Raoult's law. In an ideal solution, the vapor pressure of each component is proportional to its mole fraction. But in a non-ideal solution, this isn't always the case. Why? Well, it's all down to the interactions between the particles. In an ideal solution, the interactions between different species are equal to the interactions within the same species. But in a non-ideal solution, these interactions differ, causing the solution to deviate from the ideal behavior. Now you might be thinking, how can we quantify this deviation? That's where the concept of activity and activity coefficients come into play. Activity is a measure of the effective concentration of a species in a solution, taking into account the non-ideal behavior. It's like the true personality of a solution, hidden beneath the surface. The activity coefficient, on the other hand, is a measure of how much a solution deviates from ideal behavior. It's like the mask that the solution wears, hiding its true nature. If the activity coefficient is 1, the solution is behaving ideally. But if it's greater or less than 1, the solution is non-ideal. So, in a nutshell, non-ideal solutions are those that don't play by the rules. Their behavior is influenced by the nature of the solute and solvent, their interactions, and the conditions under which they mix. And it's through understanding these deviations, these quirks, that we can truly appreciate the complexity and beauty of thermodynamics. Remember, in the world of thermodynamics, not everything is as it seems. Let's heat things up with a deeper understanding of thermodynamics principles. In the heart of thermodynamics lie its fundamental laws. The first law, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or transformed. Imagine a steam engine where heat energy is transformed into mechanical energy to drive the pistons. Here, the total energy remains constant, it merely changes form. Moving on, we encounter the second law of thermodynamics, which introduces us to a fascinating concept, entropy. Entropy is a measure of disorder or randomness. According to this law, in any energy transfer or transformation, the total entropy of a system will always increase over time. This is why a dropped egg splatters and doesn't spontaneously reassemble itself. Last but not least, we have the third law of thermodynamics. This law states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum value. Absolute zero is the theoretical temperature at which particles have the least possible energy, and hence, the least possible disorder. These principles are not just laws, they're the fundamental truths of the universe. They govern everything from the smallest particles to the largest galaxies. They explain why ice melts, why coffee cools down, and why life as we know it can exist. Remember, thermodynamics principles are not just laws. They're the fundamental truths of the universe. They're the poetry that describes the dance of molecules, the rhythm that drives the symphony of life. So the next time you see a chemical reaction or a phase change, remember it's all about thermodynamics. So, we've journeyed through the intriguing world of thermodynamics. Over the course of our exploration, we've unearthed the profound principles that govern the flow and transformation of energy. We've navigated through the pure phases of matter, understanding how thermodynamics plays a vital role in determining their characteristics. We've seen how heat, work, temperature, and entropy are not just abstract concepts, but important players in the theater of chemistry. We've delved into ideal solutions, those perfect mixtures where components interact harmoniously. We've learned how Raoult's law helps us understand their behavior, predicting how they'll react under different conditions. Remember, in an ideal world, the vapor pressure of a solution component is directly proportional to its mole fraction. But we've also faced the reality, acknowledging that not all solutions are ideal. We've tackled non-ideal solutions, where the interactions between the components are more complex. Here, the deviations from Raoult's law give us a glimpse into the fascinating intricacies of real-world chemistry. Thermodynamics, as we've seen, isn't just a collection of laws and formulas. It's a language that describes the dance of molecules and atoms. It's a lens through which we can view and comprehend the workings of the universe, from the reactions in a test tube to the combustion of a star. For all the chemistry enthusiasts out there, understanding thermodynamics is not just a necessity, it's a privilege. It allows us to delve deeper, to question, to explore, and to truly appreciate the beauty of chemistry. To sum it up, thermodynamics is fundamental. It's the foundation upon which the magnificent edifice of chemistry is built. It's the thread that weaves through every reaction, every phase change, every interaction. And it's the key that unlocks the door to a deeper understanding of the world around us. The next time you see a chemical reaction or a phase change, remember, it's all about thermodynamics. Let's bring it all together with some real-life applications of thermodynamics. You might be surprised to learn just how much we owe to the principles of thermodynamics. Take engines and refrigerators, for instance. The heat engines in our cars and the refrigeration systems in our homes are direct applications of the principles of thermodynamics. They work on the principle of converting heat into work, and vice versa, governed by the laws of thermodynamics. In the case of a refrigerator, heat flows from a cooler to a warmer body, which seems counterintuitive but is made possible by an external work source, your refrigerator's compressor. Meanwhile, your car's engine does the opposite, converting heat energy from burning fuel into mechanical work. Moving on, let's talk about heat transfer in everyday life. Remember when you last touched a metal object on a scorching summer day and felt the intense heat? That's conduction at work, a fundamental concept in thermodynamics. The metal, being a good conductor, absorbs heat quickly and equally quickly transfers it to your hand. Finally, let's not forget the role of thermodynamics in climate change and renewable energy. The greenhouse effect, which is causing our planet to warm, is essentially a thermodynamic process, with heat being trapped by greenhouse gases. Meanwhile, solutions to combat climate change like solar panels and wind turbines also rely on thermodynamic principles to convert solar and wind energy into electricity. In conclusion, thermodynamics is not just a branch of science. It's a crucial part of our everyday lives. It's the invisible hand that powers our cars, cools our food, warms our planet, and could hold the key to a sustainable future. So, the next time you think about thermodynamics, remember, it's not just about the formulas and the laws. It's about the world around us, the energy that powers it, and the principles that govern it. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.